Good morning, students. Am I audible to you all? Am I audible to you all?
Yes, ma'am.
Is the screen visible? Screen. Is it visible?
No, ma'am.
No?
Yes,
Now?
yes, ma'am. Now visible, ma'am.
Okay. So good morning, students. Today we shall start with the last module of this subject, that is module 5, design of columns and footings. So initially we shall discuss only the design of columns. Later on we can start with the design of footing. So let's start with the session number 41 of module 5. So before we start up with, we need to understand, before we start up with the design of columns, we need to understand what exactly is this column. What is the difference between the beam and the column? So beam, we can say that it is a flexural member because the major portion or the major criteria to consider for the design of beam is the bending action as the flexure. Here we can consider this column as a compression member. We can consider this column as a compression member, and here the effective length of which exceeds 3 times the least lateral dimension. 3 times the least lateral dimension. Least lateral dimension in the sense, if I say so, if I draw a column here, this is along the length. But if I take up the cross section, horizontal look, say consider it is a rectangular column which is having the rectangular cross section. If this is rectangular in nature, then we can say that these are the lateral dimensions. These are the lateral dimensions, length and the breadth along the cross section, and this is the total height of the column. So the total height, we can consider it minimum 3 times more than that of the least lateral dimension. Now, the compression members whose lengths do not exceed 3 times the least lateral dimension may be made up of plain concrete. So, here column is to be reinforced with steel. So, we can consider it as a RC column, reinforced concrete column. But if the compression member is having the length which is not exceeding 3 times the least lateral dimension, which is not exceeding 3 times the least lateral dimension, then it may be considered, or it may be made up of plain concrete also. For example, it can have a pedestal. We can consider it as a pedestal compression member. Pedestal in the sense, you might have seen the flagpole. Flagpole ಕೆಳಗಡೆ you'll be having a concrete base. That base we can call it as a pedestal. That base we can call it as a pedestal. And a column forms a very important component of a structure, because usually if it is a building with the columns, then the load from the slab it is transferred to beams, and from beams it is transferred to columns, and from columns it is transferred to footing, and then to the earth, that is soil. And these columns support beams, which in turn support walls and slabs. As I said now, it should be realized that the failure of a column results in the collapse of the entire structure, and the design of column should be of most importance. And here the column is a vertical structural member which is supporting the axial compressive loads majorly, and it may be with or without the moments. So depending upon whether it is considered with the moments or without the moments, we can classify the columns, and that will be discussing later. And the cross sectional dimensions of the column, they are generally considerably less than that of its height, as I said before. And columns support vertical loads from the floors, roof, and transmit these loads to the foundations, or we can call it as footing. So the more general terms, compression members and the members subjected to combined axial load and bending, they are sometimes used to refer as columns and walls and the members in the concrete or the frames. So these may be vertical, it may be inclined or it may be horizontal. So column is a special case of compression member which is vertical. Here in case of column we can have the vertical member, and the stability effect must be considered in the design of compression member. So this is criteria we need to consider at most. The stability effect, the stability of a compression member is of most important in the design. So with this background, let's proceed with the classification of the columns. So the classification may be based upon different criteria. The first one is based upon the shape. Here we have the rectangle, square, circular, triangular, polygonal and L shape, plus shape, T shape and all. So depending upon the cross section of the column, we can define the column as rectangular, square, circular, polygon, plus the or the height upon the slenderness ratio or the height. So this slenderness ratio is of most important to be considered in any of the design of columns. So what we can do is we can say that a short column or a long column depending upon the slenderness ratio or the height of the column. Either we can say that column is short column or long column, or else we can say it to be short column or slender column. So long column means it is slender column. We can say that short and long or the slender column. So a compression member or that column may be considered as short when both the slenderness ratios. What exactly is slenderness ratio? How to calculate that? We'll discuss in just a while. So when both the slenderness ratios, namely LEX by D, that is the length, effective length in x direction, effective length in y direction, LEY. So LEX by D and LEY by B. This is breadth of the section, this is depth of the section. So LEX by D and LEY by D, if these both values they are less than 12, then we say that it is short column. If it is less than 12, we say that it is short column. So what exactly is LEX? LEX is effective length in respect of the major axis. LEX is effective length in respect of major axis and LEY is effective length in respect of the minor axis. LEY is effective length in respect of the minor axis and D is depth in respect of the major axis. Along the major axis, whatever the dimension comes, that we call it as D, and along the minor axis, whatever the value it comes, we call it as B, that is width of the member. So if LEX by D and LEY by B, if they are less than 12, we say that the column is short. If it is reversed, that is if it is greater than 12, then we call it as a long column or the slender column. Long column or the slender column. So this is how, based upon the slenderness ratio, we can consider the short column or long column or short and slender column. Now, most importantly, based upon the type of loading, based upon the type of loading. Based upon this type of loading, the column can be classified into three categories. That is axially loaded column or centrally or concentrically loaded column. Axially loaded column, or we can also call it as centrally loaded column or concentrically loaded column. Both, all the three have the same meaning. And the second one is the column subjected to axial load and uniaxial bending. Column subjected to axial load and uniaxial bending. Uniaxial bending in the sense you are considering bending in only one direction. You are considering bending in only one direction. And the third category is the column subjected to axial load and biaxial bending. Along with axial load, we are considering biaxial bending, that is bending in both the directions. Bending in both the directions we are going to consider. So the examples and the sketches, they are being shown here. See here, axially loaded column or concentrically loaded column means along the centroid of the cross section there is load acting. Load is acting along the centroid of the section. So we can say that it is axially loaded column. And the next one is column subjected to axial load and uniaxial bending. Column subjected to axial load and uniaxial bending. That is nothing but here we are considering axial load. Yes, along with the axial load, that is P, along with this P, we are going to consider uniaxial bending, that is bending in one direction. And when do we get this bending in one direction? When the load, this load P is not placed at the centroidal axis, it is placed at some distance from the centroidal axis. And that distance we call it as E, that is eccentricity. The distance we call it as E, which we say it as eccentricity. So the column is loaded with eccentric loading. So if it is eccentrically loaded, then we say that the column is subjected to axial load and the bending. So here it is uniaxial bending because it is only in one direction. See here. Here the cross mark you are able to see. You are able to see the cross mark. So whenever you are seeing here, it is, if you consider in the y direction, it is along the centroidal axis itself. Yes, it is along the centroidal axis, but it is deviated from the centroidal axis of this x. That is, it is deviated from this axis. So it is deviated from only one axis. So we'll have only uniaxial bending. You will have only uniaxial bending. Next, coming on to the column subjected to axial load and the biaxial bending. So if we are considering the axial load and biaxial bending, so here we have the cross section. Here the centroidal axis are being shown. This is x axis, this is y axis. And you can just see the section here or the point where the loading is being acting. Here it is displaced from both the centroidal axis. The point of loading is displaced from both the centroidal axis, even from the x axis as well as from the y centroidal axis. So here in this position we have biaxial bending because from both the directions the centroidal axis is being displayed. Centroidal axis is being displayed from both the directions. So we call it as a biaxial bending. And here we need to consider PU, that is axial load, MUX, moment in x direction, MUY, moment in y direction. Okay, now considering the specification for covers and the reinforcement in column. Specification for covers and the reinforcement in column. For a longitudinal reinforcing bar in a column, the nominal cover shall be in any case not less than 40 mm. The cover should not be less than 40 mm or less than the diameter of such bar. less than the diameter of such bar. So in case of columns, the minimum dimension of 200 mm or under, and whose reinforcing bars do not exceed 12 mm, a nominal cover of 25 mm may be used. Nominal cover of 25 may be used. But usually the dimension of the column exceeds 200 mm. So you need not use cover of 25 mm wherever you are designing in this subject, at least, wherein we are going to use the cover of minimum 40 mm. Of footings we are using a cover of 50 mm. And nominal cover in mm to meet the durability required is decided based upon the exposure conditions. Based upon the exposure condition. And for the mild it is 20, moderate 30, severe 45, very severe 50, extreme 75, and so on. Okay, now the nominal cover to meet the specified period of fire resistance for all fire rating 0.5 to 4 hours is 40 mm for columns only. Now considering the effective length of the compression member. Effective length of the compression member. So even in the beams, slabs, stairs and all, we have calculated the effective length for which we need to do the design. Here also we need to consider the effective length. So how we need to consider the effective length for in case of column? So for the column or the strut, column or a strut, strut is nothing but a compression member. Strut is a compression member. Instead of compression member, we can in short write it as a strut. Strut is a compression member, the effective length of which exceeds 3 times the least lateral dimension, as we have defined in the previous. And for the normal usage, assuming idealized conditions, the effective length of in a given plane may be assessed based upon the basis of table 28 of IS 456-2000. Based upon the table 28 of IS 456. Let me show you IS 456, table 28. Yes, here is the table 28 of IS 456, wherein we have the effective length of the compression members. We have effective length of the compression members. So according to that, degree of end restraint of the compression member. Following end restraints, what are the different conditions, different cases? These are the different conditions or different cases what we can have. Effectively held in position and restrained against rotation in both the directions. Effectively held in position and restrained against rotation in both the directions. Effectively held in position at both ends and restrained against rotation at one end. Effectively held in position at both the ends but not restrained against rotation. Effectively held in position and restrained against rotation at one end and the other restrained against rotation but not held in position. Similarly, we can have here also. Effectively held in position and restrained against rotation in one end and at the other, partially restrained against rotation but not held in position. Effectively held in position at one end but not restrained against rotation and at the other end restrained against rotation but not held in position. Effectively held in position and restrained against rotation at one end but not held in position nor restrained against rotation at the other end. So depending upon these criteria, we can use the recommended value and the theoretical value of effective length, and the picture or the representation of such kind of restraint is being given here. effectively held in position and restrained against rotation in both the ends. Means both the ends they are held in position and they are restrained against a rotation. Means there is no possibility of the rotation at the two ends. No possibility of rotation at the two ends. And here, effectively held in position at both the ends and restrained against a rotation at one end. So they are held in position both the ends, but one end is restrained against rotation, but the other end is having a hinge and there is possibility of the rotation. So similar way we can define all other end restraints. The same thing is being here. Here there is a hinge, so it can be possible for the rotation. So here also effectively held in position. They are held in position, but they are not restrained against the rotation. Means both the ends are hinges. So this is how we can use this table whenever we are given with the condition of the column, whether it is restrained in position, whether it is being not restrained in position, and so depending upon that we can use the effective length. Now coming on to the unsupported length. The unsupported length of the compression member shall be taken as the clear distance between the end restraints. Clear distance between the end restraint, and exception to this is for the flat slab construction. So this is not there, we are not going to study for flat slab. So you can just consider that the unsupported length of a compression member shall be taken as clear distance between the end restraints. And now coming on to the slenderness limits for the columns. Slenderness limits for the columns. The unsupported length between the end restraints shall not exceed 60 times the least lateral dimension of the column. The unsupported length between the end restraints shall not exceed 60 times the least lateral dimension of a column. These specifications they are there in the IS 456 also. And if in any given plane one end of the column is unrestrained and its unsupported length shall not exceed 100 b square by d, where b is the width of the cross section and d is the depth of the cross section measured in that plane under the consideration. So depending upon these cases we can decide the slenderness limits, and this is there in the clause 25.3. Clause 25.3. Yes, effective length of the compression member. So here we have the slenderness limits for the columns, and the same thing we are going to use it in the numericals. And even for the unsupported length we have the codal provisions here, we can refer it. And here for the compression members definition we have short and slender column members. So depending upon what criteria we are going to decide the short column and the slender column, that is there. And here we have unsupported length, the provisions, effective length, slenderness limit, and lastly we have the minimum eccentricity. So according to code, the specifications as per IS 456 for the longitudinal reinforcement. For the longitudinal reinforcement, the cross-sectional area of the longitudinal reinforcement shall be not less than 0.8% nor more than 6% of the gross cross-sectional area of the column. And use of 6% reinforcement may involve practical difficulties in placing. So hence lower percentage of reinforcement is recommended. And In any column that has longer cross-sectional area than that required to support the load, the minimum percentage of steel shall be based upon the area of concrete required to resist direct stress and not upon the actual area. So here minimum percentage of steel shall be based upon the area of concrete required, that is AC. We call it as A with the prefix subscript C. And the minimum number of longitudinal bars provided in a column shall be 4 in rectangular columns and 6 in circular columns. Minimum. So if it is a rectangular or a square column, minimum number of bars they are to be 4, and if it is a circular column, we should have the minimum number of 6 columns. Sorry, 6 reinforcement bars. And the bar shall not be less than 12 mm in diameter. Minimum diameter of the reinforcement in column, we need to use it as 12 mm. So we cannot use 10 mm bars, 8 mm bars for the longitudinal reinforcement. And a reinforced concrete column having helical reinforcement shall have least 6 bars of longitudinal reinforcement within the helical reinforcement. If the column is circular in nature, we will be having the helical reinforcement. And here minimum number of bars we need to use is 6. So minimum number of 6 bars are to be used. Whatever the dots I am showing, they are referred to as the longitudinal reinforcement. They are referred to as longitudinal reinforcement. And the spacing of longitudinal bars measured along the periphery of the column shall not exceed 300 mm. And in case of pedestals, in which the longitudinal reinforcement is not taken into account in the strength calculation, nominal longitudinal reinforcement not less than 0.15% of the cross-sectional area shall be provided. So here if we see the longitudinal section, this is along the length of the column, and these horizontal bars, these are called as the lateral ties. These are called as lateral ties, and this vertical bar, it is being called as longitudinal bar, and the spacing between the lateral ties, we call it as the pitch of the lateral ties. And this distance from this bar to the face of the column, we call it as cover to lateral ties as per the IS 456. And the transverse reinforcement, a reinforced concrete compression member shall have transverse or helical reinforcement. As I shown in the previous, helical reinforcement, circular reinforcement, so dispersed that every longitudinal bar nearest to the compression face has effective lateral support against buckling. Effective lateral support against buckling. Buckling in the sense, if the length increases, there is possibility of buckling, and that buckling criteria should be avoided. And the arrangement of transverse reinforcement is shown here. So depending upon, if the column is having more number of bars in one direction, then we can have the lateral ties in both the directions. Here there is one lateral tie, and here there is one more lateral tie. So there are 2 lateral ties, so totally there are 4 legs. So depending upon that, we can define the reinforcements. And coming on to the pitch and diameter of lateral ties. How should we decide this pitch and the diameter of lateral tie? The pitch, that is the pitch of the transverse reinforcement, shall not be more than the least of the following distances. That is the least lateral dimension of the compression member and 16 times the smallest diameter of the longitudinal reinforcement bar to be tied and 300 mm. So least lateral dimension of the compression member, whether it is in x direction or y direction, that dimension, and 16 times the smallest diameter of the longitudinal reinforcement. If we are using 12 mm bar and 20 mm bar, out of these two, smallest diameter is 12 mm. So 16 times 12 mm that we need to consider, and 300 mm. So out of this, whichever is less, that distance we can consider. And the diameter. The diameter of the polygonal links or ties shall not be less than 1/4 of the diameter of the largest longitudinal bar. Suppose we are using 25 mm bar, 25 mm bar, then 1/4 of 25 mm. 1/4 of 25 mm turns out to be 6 mm or more, and in no case less than 6 mm. So if it is 6 point something, we can proceed with 8 mm diameter. And if it is less than, suppose we are using 20 mm diameter of longitudinal bar, then 1 by 20 by 4, we are getting 5 mm. So we cannot use 5 mm, we can go ahead with minimum 6 mm. Minimum diameter of the lateral ties is 6 mm, or it can be of more diameter also. And for the helical reinforcement, the pitch helical reinforcement shall be of regular formation with the turns of helix spaced evenly, and its ends shall be anchored properly by providing 1.5 extra turns of the spiral bar. So again, at last we have the limit state of collapse for the compression members. For the compression members, and these are the assumptions to be made according to IS 456. That is, the maximum compressive strain in concrete in axial compression is taken as 0.002. The maximum compressive strain at the highly compressed extreme fiber in concrete subjected to axial compression and bending when there is no tension on the section shall be 0.0035 and minus 0.75 times the strain at the least compressed extreme fiber. And plane section remains plane even after bending. That is a common criteria which we are observing. And the maximum strain in concrete at the outmost compression fiber is taken as 0.0035, which is same as that of flexure. And the relationship between the compressive stress distribution in concrete and strain in concrete may be assumed to be rectangular, trapezoidal, parabola, or any other shape which results in prediction of strength in substantial agreement with the results of the test. And here the tensile strength of the concrete is being ignored, and these are the following. These are the different assumptions what we can have in case of limit state of collapse. And finally, we have the minimum eccentricity. For the minimum eccentricity, as per the IS 456, all the columns shall be designed for minimum eccentricity, that is equal to the unsupported length of column divided by 500 plus lateral dimension divided by 30, that is L by 500 plus D by 30, subjected to a minimum of 20 mm. Where biaxial bending is considered, it is sufficient to ensure that eccentricity exceeds the minimum about one axis at a time. And short axially loaded members in compression. The member shall be designed by considering the assumptions of the code book and the minimum eccentricity as we have just studied this codal provision, and it does not exceed 0.05 times the least lateral dimensions. And to use that, we have this equation to consider, that is Pu is equal to 0.4 FCK into AC plus 0.67 Fy into ASC. That is Pu is axial load on the member, FCK is characteristic compressive strength of the concrete, AC is area of the concrete, Fy is characteristic strength of the compression reinforcement, and AS refers to area of longitudinal reinforcement for the columns. So this is how we need to consider the design criteria. And in the next session, we are going to start up with the numerical examples where we are going to design the columns with axial load, that is concentrically loaded member. So the first case we are going to study there. And here we have the reinforcements details. You can have slenderness limits, and let me show you the transverse. Yes. For the columns, yes, 26.5.3. Here we have the different clauses for the longitudinal reinforcement. We have the clauses for the transverse reinforcement and arrangement of transverse reinforcement. Then coming on to the pitch and the diameter of lateral ties and the diameter, helical reinforcement, and so on. So these clauses we are going to use it for our design and do the design for axially loaded member only, that is concentrically loaded column. But if we are supposed to design the axially loaded column along with uniaxial bending and biaxial bending, there we are supposed to consider one more code, that is SP16, that is which is a design aid for IS 456. Therein we are going to use many of the graphs. Depending upon those graphs, we are going to do the design for column subjected to uniaxial bending and biaxial bending. So in the next session, we'll start up with axially loaded column numerical examples. So now we shall end up with this session, and let's meet in the next session. And at the codal provision, I feel you should have a soft copy at least of IS SP16. If not, I'll be posting it in the group, soft copy of SP16. Please keep one copy of SP16 along with you. Okay, that's all for today. Thank you.